Today we're going to talk about something called electromagnetic induction. And induction is just creating a current without using a battery, but actually using a magnetic field. So imagine that I have a loop of wire and I put it inside a magnetic field like this. And it turns out that if I move it through the magnetic field, I will create a current even though there's no battery, there's no generator, there's nothing. But it's the movement in the magnetic field that will create the current. And I will show you how this works, but first I think you probably need a little bit of a review of magnetic fields. So I'm going to do that first, and then we're going to start with induction. Alright, so let's start with a very simple question. Imagine that I have a positive charge that's still here in a magnetic field that is pointing to the right. My question is, where does the force go? So is it going to be proportional to the charge, to the field? Is it going to point this way, this way, this way, this way? Stop the video, think for 10 minutes, give me an answer. Alright, hopefully you did what I asked you, and hopefully you did not answer the force goes this way, because the magnetic field works weird and the force is always perpendicular to the magnetic field. But not only this, I just told you that this thing is not movement. It's not moving. And the magnetic field is a field that needs movement. It does not affect things that are not moving. The charge of the magnetic field is a moving charge, not a charge, which means that this receives absolutely no force. So force equals 0. There's no force. Now, if the charge is moving, let's say that the charge is moving this way, and the magnetic field, it's superimposed, but I'm not going to draw it superimposed just so that you can see both, is pointing this way. Now, where does the force go? Again, give yourself 10 minutes, pause the video, and answer. Alright. Well, again, if you gave any answer that's not 0, then you gave the wrong answer, because remember that the force has to be perpendicular to both the magnetic field and the velocity. So when the velocity and the magnetic field are parallel, then there's no force. Period. Now remember that if we wanted to calculate the direction of the magnetic field, we had several options. We could use the left-hand rule, we could use this fist rule that I showed you, but the idea is that you will always have a force that's both perpendicular to both V and B. Now, one more thing that we need to remember is the actual value of the force. And remember that that was the magnetic force equals the charge times the velocity times the field. But remember, only the component of the field that's perpendicular to the force. So call it By, B, whatever you want. Alright, we're now in a position to consider what happens, for example, to a single wire going down at a constant speed in a magnetic field. And remember that this means that the magnetic field is coming out of the page, so coming towards you as you're watching this. Alright, so in here we have a bunch of charges, right? We have protons, we have electrons, and these are moving because I'm moving them downwards, and therefore I have the two conditions that I need for a magnetic field. I have a charge, and the charge has a velocity. And not only this, but the velocity is perpendicular to the field, which remember is coming out at me. This means that there will be a force on the charges in here that will push them to one side. It doesn't matter what side. All we need to know is that the side is going to be perpendicular to both V and B. So let's just say that the force goes this way, and either the protons or the electrons are going to go this way, and then if the protons go this way, then the electrons are going to go this way. Which means that then I'm going to have a charge excess here and here. And of course that's going to create an electric field. Now, to this electric field I can of course associate a potential difference, which is just, well, all we need to do is remember that E is V over L, or that V equals E times L. Just if you have a constant field in here, then remember work equals force times length, and therefore potential, which is work per unit charge, is field times length, because this is also force per unit charge. Okay? So this is going to be our potential based on the field. And now I ask myself, okay, so what's the electric force on an electron here? Well, the electric force is, of course, E times the field, or E times V over L. And once this is going down, once this is in equilibrium, this is stable, this force has to be exactly equal to the magnetic force on these same charges. Otherwise, there would still be movement. Right? So once this has stabilized, this is going down, a potential difference has been created, there's no more movement, means that this thing has to compensate the magnetic force. Now, the magnetic force, remember, is QVV, and in this case, V is just this V, and Q is also the charge of the electron. So we have that these two things have to be equal. Alright, so let's see what we get. So we have that EV over L has to be equal to EVB. Now, of course, we can cancel this out, and then we have that there's an induced potential difference of VLB. And this is huge, because we found out a way of creating a potential difference without using anything but a magnetic field. And magnetic fields are really easy to make. All you need is a magnet. So we can create a potential difference, which is very, very useful, because we can use this for all kinds of devices just with a magnetic field by moving a wire in it. And that's something. Now, if you don't believe this is true, or if you want some further evidence, we can check whether the units actually check out. And the way to do this is to realize that V and B together are units of force per unit charge, right? Because the magnetic force is EVB. So EVB without the E, then VB is force per unit charge. So then we have force per unit charge times unit of length, and then units of force and length together, that's work. So that's work per unit charge, which is potential. Ta-da! The units check out. Now, let's take a look at this for a second and try to see if we can generalize this somehow. We have a potential that's proportional to the speed of the wire moving through it, to the length of the wire, and to the field. Now we can ask ourselves, how could we make this bigger? Well, we could, for example, make the wire move faster, or we could make the wire longer, or we could make the magnetic field stronger. And if you do other experiments, for example, instead of using this wire, you use a closed loop of wire, you could also calculate this, and you will see that the potential actually depends on the area of this loop of wire. And here we couldn't have an area because we just had a wire. And Michael Faraday, Faraday, I've always called him Faraday, but probably that's because I'm Spanish. Well, Michael Faraday kind of realized this and saw a bunch of other experiments and summarized his findings using something called magnetic flux. And the idea of magnetic flux is actually pretty similar. It's very similar to water flux, really. So imagine that I have a loop of wire and there's a magnetic field going through it. So these are magnetic field lines. Now the magnetic flux is basically defined as the number of magnetic field lines that are crossing a certain surface. So, for example, imagine that I have a surface like this, and I have a magnetic field that goes through it. So what I do is I take a look at the number of field lines that cross the surface, and that's called the magnetic flux. Now, this is of course a little vague, but there's a much more precise way of defining this mathematically. And the way to do this is the following. We just take the field, so we say this is the flux. Now the flux is of course proportional to the field and proportional to the area, so we just multiply them together. And it would look like we're done, but we're not quite there yet. Now imagine that So I'm going to take this, but just make it 2D. So here's my surface. It's just that I'm looking at it from the front. Okay? But this is exactly the same thing as this, just from the side. And now let's say that there's a bunch of magnetic field lines coming through. Now as you can see, not all the field lines go through the surface, right? What we really care about here are the ones that are normal through the surface. So, because for example, if my surface was like this, then no field lines would cross it, right? So the flux can't be proportional to just the field and the surface, but it's actually proportional to the field, the surface, and the fact that if I tilt this, I get less flux. Now, how do I account for the fact that there's less flux? Well, I can do the trigonometry and figure it out, or I can just do it in a much more quick and dirty way, which is, okay, let's just call this thing here the normal to the surface. Okay, it doesn't matter if it's this way or this way. Okay, and then I ask myself whether the normal to the surface is parallel or perpendicular. So in here, the normal to the surface is perpendicular, and in this case I get zero flux. So sine or cosine, when it's 90 I get 0. Well, that's a cosine, right? And here, when the normal to the surface is parallel to here, so 0 degrees, I get maximum flux. Again, cosine of 0 is 1. So obviously I need to put the cosine here. So cosine theta. And it would look like I'm done, but I'm actually still not done, believe it or not. Now what can also happen is that I have one surface, but it's stacked on top of other ones, or just like a loop, right? Just like this, 1, 2, 3, 4, 5, 6, and so on. And so I have n loops. And now, of course, what I have now is n surfaces. So the field lines go through 1, 2, 3, 4, 5, 6, and so on until n surfaces. So I need to take this into account. So if I have n loops of wire, then I need to take this into account and put it in here. And that's how I get the formula for the loop. For the magnetic flux. The magnetic flux is proportional to the number of wires, the field, the area, and careful, the cosine of the angle, because it's not the same to be like this than being like this. Now, we need to speak about units for a second. The units of magnetic flux, as you can see, the only thing that has units here is B and A. So, of course, the units of magnetic flux, remember this means units, are going to be Teslas from the magnetic side, and then square meters from the area side. Now, remember, this is multiplying, this is not dividing. But because this is a little ugly as a unit, we baptize it as the Weber. So magnetic flux is measured in Webers. Now, how can I use this flux thingy to determine the potential that I induce magnetically on a wire or on a loop of wire? Well, let's take a look at this again. And here the key is that there's a velocity, right? If I had a loop of wire in a magnetic field, sorry, a loop of wire, just a wire, and it didn't move, then no charges would move. Therefore, there would be no magnetic force. Therefore, there would be no induced current. So what seems important is not so much the fact that there's a magnetic field or that there's a flux, but that there's a change in this. And that's what Faraday discovered. Faraday discovered that the potential generated is actually proportional not to the flux, but to the change in the flux. And we can express this mathematically, saying that the generated EMF, and remember that EMF is just the energy generated per unit charge, which is kind of the same as potential difference, but not exactly, is just equal to the increase in flux per unit time, with a minus sign here. Now in the book you will see that there's an n in here, but this n is this n here. So I think that the book has double counted the n. If you put the n for the flux, then you don't put an n here. If you're just counting the flux of one loop of wire and you have several, then of course you need to include the n in here. Now we can turn this formula into a derivative simply by turning the increments into differentials. So actually the formula that really goes, even though you won't have to use it, or it's very unlikely that you will have to use it, is that the EMF is the derivative of the flux respect to time. They both will work 90% of the time. However, if the increase in time is not linear, then you're forced to use this one. Now let's use what we just derived to solve a very, very simple problem involving a variable loop of wire. So imagine that we have this wire here that is closed, and here there's a mobile spot. So this is moving along the wire at a certain speed, v. So v. And we want to know what the EMF is going to be in here. Of course, there's a magnetic field coming out of the page. It really doesn't matter if it comes out or in of the page. We will get exactly the same magnitude for this. Alright, so the first thing that we need to do is calculate the flux. So the flux is going to be the area. So the area times the field, and in this case we don't have any loops and the angle is already 0 degrees, so that's it. Now the area, of course, we can set it as a function of this length and of course this width. I'm just going to call it A. So then the area is just going to be A times this side over here, which is L minus Vt. So I've got A times L minus Vt times B, and that's ALB minus AVBT. And now all I need to do to find the EMF is use one of these two formulas. You could use either. I'm going to use this one simply because it's easier, but you would get exactly the same result no matter what you did. So let me zoom out so that we can see this better. And I'm just going to take the negative of the derivative with respect to t. So minus d of the flux dt equals, now this is a constant, so the derivative is 0. This is multiplying t, so the derivative is just whatever multiplies t. So I'm going to get AVB, which is equal to the EMF. And that's it. So again, simple steps. Calculate the flux, derive the flux, get the EMF. Now let's take a look again at the example we just did. And I'm going to change the orientation of the field just because it makes things easier. But we would like to know not only the EMF that we generate, but in which direction the current is going. So is it going this way or is it going this way? And we can deduce this, but there is a law that will give us the answer in a much more straightforward way. So first thing, we're going to deduce this straight, and then we're going to turn this into a law that we can just use for any case. Now let's think about this for a moment. When I move it this way, so I move this way, let's imagine that this creates a current that goes like this, okay? So positive charges moving this way. So now I ask myself what the magnetic force is going to be on the charges that are moving this way. Okay, well, the field goes this way, the velocity goes this way, and now all we need to do is use the technique that I showed you to find out the force. And if you do it with the right hand, and remember that your knuckles point in the direction of the speed, and then your fingers point in the direction of the field, then you get that the force should be pointing this way. Which means that if I start pushing this a little bit, then I can stop pushing, because then a force will continue to push this in this direction, giving in more and more and more and more energy without me doing anything at all. And not only it's giving this more and more energy, it's also giving this more and more current because it is moving faster, and I'm getting all this for free. Which means that I just found out a way of getting free energy. Now, of course, that's not possible. And because that's not possible, this cannot be the case. And therefore, this cannot be the case. And what has to happen is the current goes exactly in the opposite way, creating a force in exactly the opposite direction, this way, opposing the one that I'm doing, putting this way. Why? Because otherwise energy wouldn't be conserved. I would find a way of getting free energy. Now let's look at what this thing is doing. This thing is actually pushing me in exactly the opposite direction that I'm trying to change the flux. So I'm trying to push this way to reduce the flux, and this is creating an EMF that creates a force that's making me push the exact opposite way. It's trying to cancel out my pushing. And this makes sense. This means that if I want to create an EMF here, I need to do a force to push this thing here. And it's exactly the force that I need to do to counter this that allows me to give energy to this. So when I have an induced current, I'm not getting energy for free. The energy that I'm getting it because of the mechanical work that I'm doing in trying to move the wire or the magnet. And then the opposing force that the current does to me, I have to overcome, and that's what's giving me the energy to obtain the current through the wire. Now, we can make this more precise, and this is what Lenz's law is. Lenz's law says every time that I try to change the flux, the induced current will be such that it will try to counter the change in flux. So if I'm trying to reduce the flux, this will create a current that will create flux the opposite way. It will try to increase the flux, and so on. So for example, this reduces the flux. So how could I possibly increase the flux? Well, I could increase the flux by creating a magnetic field that goes out of the page. And that is precisely what will happen if I let the current flow this way, therefore cancelling what I'm trying to do. So every time that I try to change the flux, the induced current will try to change it the opposite way that I am changing it. Now, here's a written statement so that is much more precise so that you can just see the law as it is written. It popped out of nowhere. Okay, so I know that this sounds a little bit confusing, so let's apply it to an example to see if we can understand what this means. Now imagine that I have a magnet that creates a magnetic field that goes in this direction, and here I have a loop of wire. And what I try to do is to approach this magnet to the wire, and I want to know the direction of the current in the wire. Well, since I'm trying to increase the magnetic field down, the current here will be such that it creates a magnetic field up. And remember, to do that, we'll use the right hand rule, which is you just curl your hand around the wire with your fingers pointing, and then your fingers will point in the direction of the current, your thumb will point in the direction of the field. So using this, we can see that this will generate a current this way, according to Lenz's law, because it's the only one that will counteract the increase in the field going down. Now, if we did the opposite thing and we made this thing go up, then we would be decreasing the field going down, so then the current would flow the other way around in order to increase it, because we're doing the opposite thing. I hope it's much clearer now. Well, that's all for today. Hope it wasn't too rough. After this, you should know how to calculate the flux, you should know how to calculate the EMF using the flux, and you should know how to find the direction of the induced current using Lenz's law. Everything else is just doing this over in different ways. Now, again, of course, we will tell whether you understand this when we start doing the problems. Good luck!